Hello and welcome. In the last video, we talked about what extrema are, what a relative extrema is, and what an absolute extrema is. And we talked about identifying them from the graph of a function. And then we moved into how to find a critical number and how to use critical numbers to determine where a function is increasing, decreasing, and where it has relative extrema. What we're going to do in this video is first review that last idea, how to use the first derivative test. And then we're going to extend that idea a little further to, now that we know how to find relative extrema, how do we find absolute extrema over an indicated interval? So what I'm going to encourage you to do first is go ahead and find the critical numbers for numbers 4 and 5. So find the derivative, set it equal to 0 so that you can find those critical values. And then unpause the video and see how you did. So hopefully you had time to work through the first part here. The derivative on number 3 is 3x squared minus 6x plus 3. We care about where this derivative is undefined, which this is defined everywhere because it's a quadratic. So there's no discontinuities, there's no x values we can't plug in. So it's defined everywhere. So then the only thing we need to consider for our critical values is where this is 0. So I'm going to go ahead and factor a 3 out here. And then I'm going to divide that 3 on both sides. So I'm going to get 0 equals this trinomial, which I'm going to factor. That's going to be x minus 1 quantity squared. So the only critical number that we have is x equals 1. I'm going to finish up that same process on number 4. So here we have the derivative. The derivative of x is 1. The derivative of negative 2 sine of x is negative 2 cosine of x. So this is also defined everywhere. Cosine is defined everywhere. So the only critical numbers, or the only possible critical numbers, would be what I get when my derivative is equal to 0. So if I set this equal to 0 and I subtract 1, and divide by negative 2 on both sides, I'm really trying to figure out when is cosine of x equal to 1/2. So if I'm thinking about that in terms of my unit circle, cosine is the x value. That's equal to positive 1/2 here and here. So that means x is pi over 3 or 5 pi over 3. So the very first thing we need to do to talk about extrema and intervals of increasing and decreasing is find the critical values. And the critical values, or the critical numbers, are where the derivative is undefined or 0. Once we have identified those critical numbers, we want to look at them on a sign chart or a number line. So I'm asking myself, what's a friendly number, a nice number that's smaller than 1 that I could plug into my derivative? Not my original function, but my derivative. So I like the number 0 a lot. 0 is smaller than 1. If I plug 0 in here, I'm getting 0 minus 0 plus 3. So that is a positive number. Then I need something larger than 1. If I plug in something like 2, I'm getting 3 times 2 squared. So 3 times 4 is 12, minus 6 times 2, 12 minus 12 plus 3. That's going to also be a positive value. Now that I have my sign chart, I can talk about the behavior and the extrema of our function. Anywhere that the first derivative is positive, the function is increasing. Well, that is actually happening everywhere. That means that our function is always increasing from negative infinity to infinity. You'll notice that we do have a critical number at 1. That means that something is going on at 1, but it's not changing the behavior of the function. And it should make sense that this function is always increasing. This is some sort of cubic function, right? It's x to the 3rd power. And that does make sense that it's always increasing and that something sort of odd is happening at 1. Always increasing, since f prime of x is always positive or always greater than 0. There are no relative extrema because a relative extrema only happens when the derivative is changing sign, and since it's positive everywhere, it's never changing sign. Now let's go back to number 4. So we need to make a sign chart or a number line with h prime. And we're going to I'm going to redraw this. This specific problem is telling us that we're only looking at the intervals from 0 to 2 pi. I'm going to put that on my number line so that I don't accidentally try and say negative infinity like I did over here on number 3. So 0, and then our critical values, pi over 3 and 5 pi over 3. I need to plug in a number between 0 and pi over 3. So I'm going to choose the pi over 4 angle, and pi over 4 I know for cosine and sine is root 2 over 2. So I'm going to plug that into my derivative. So h prime, and you don't necessarily have to show this work, right? Because we only care about the sine. This is going to be 1 minus 2 times root 2 over 2. So this is going to be 1 minus the square root of 2. I don't care what this number is, I just care if it's positive or negative. Well, the square root of 2 is definitely bigger than 1, so this part of my graph is going to be negative. Now I want to pick a number somewhere between pi over 3 and 5 pi over 3, so somewhere between here. And I'm going to pick pi over 2, which is up here, and I'm going to pick pi over 2 because I know that cosine is 0 there, so that seems like it's going to make my life a little easier if I plug in pi over 2. H prime of pi over 2. Here we go. So cosine of pi over 2 is 0. 1 minus nothing is going to be 1, which is positive. And then last but not least, I need to pick something in this region over here. So I am going to choose 7 pi over 4 so that I can again use that root 2 over 2 point. So I'm going to say h prime of 7 pi over 4 is equal to 1 minus 2 times root 2 over 2, because that's what cosine of 7 pi over 4 is. So I'm back to 1 minus root 2, which we already said is negative. So anywhere that our derivative is negative, our function, our original function, h, is decreasing. So it's decreasing between 0 and pi over 3, and between 5 pi over 3 and 2 pi. And we're going to justify that by saying, since not f, but h prime is negative. And you could write the word negative as well. It's increasing where this sign chart, where this number line is telling us that we have positive values for our derivative. So it's increasing between pi over 3 and 5 pi over 3, since h prime of x is positive there. We do have extrema. So originally, between 0 and pi over 3, our function is going down, it's decreasing, and then it starts going up. That means we have a relative minimum there, a relative min. And this question specifically asks us to write them as ordered pairs. So there's a relative min at pi over 3. If I plug in pi over 3 to our original function, I'm going to get pi over 3 minus 2 times sine of pi over 3, which is going to be pi over 3 minus the square root of 3. And we can leave it like that. Between at 5 pi over 3, this was increasing and it starts decreasing. So we also have a relative max at the point 5 pi over 3, comma, 5 pi over 3 minus the square root of 3. So our relative min is happening because h prime is changing. I'm going to use a delta symbol for changing from negative to positive. And we have a relative max because h prime is changing from positive to negative. So make sure you have those justifications there. They're important. Now that we have reviewed a bit about relative extrema, let's go back and talk a little further about absolute extrema. We talked about in the last video that absolute extrema only occur, we can only consider them when we have a closed interval. And what we're going to use to identify them is something called the candidate test. So the candidate test basically says the absolute extrema either happen on the endpoints or at one of the relative extrema. So what that means is anytime we're looking for the absolute extrema, we're going to find our critical numbers, and we're going to test our critical numbers and the endpoints in a table to figure out which of those numbers makes our original function the largest and which of those numbers makes our original function the smallest. So let's look at some examples. Here we have this interval, and we are being given this function. So the first thing we need to do is find our critical value. So we're going to take the derivative. So I have 1/3 times, if I take the derivative here, I get 3x squared. And if I take the derivative of 2x squared, I get negative 4x. We want to know when this is 0. So I'm going to simplify this a little bit. This is just going to be x squared minus 4x. I can factor out an x here. So that's going to give me x equals 0 and 4. Those are my two critical values. So I want to make a table with the candidates for the absolute extrema. The highest value of the function and the lowest value of the function. I need to include the endpoints, so -1 and 3, and then I also need to consider any critical value that's within that interval. So we found two critical values. We found 0 and we found 4, and 4 is not in the interval. So we don't need to consider that when we're looking at our absolute extrema. So I'm going to add 0 over here because 0 is within that interval. Now what I'm going to do is I'm going to take all three of these x values and I'm going to plug them into the original function, f of x equals 1/3 of x cubed minus 2x squared. So if I plug -1 in, I get -1/3 minus 2, which is -7/3. So I'm going to go over to my table and I'm going to add -7/3. If I plug in 0, I get 0. If I plug in 3, and remember we're plugging these into the original function, not the derivative that we found. If I plug in 3, I get 3 to the third is 27 divided by 3 is 9. 2 times 3 squared is 18. So 9 minus 18 is -9. So these are the only three values that could possibly be the absolute extrema. So all I have to do now is ask myself, what is the largest of these numbers? That is the absolute max. In this case, the largest of those numbers is 0. The absolute maximum is 0. What is the smallest of these numbers? The smallest of these numbers is -9. So the absolute minimum is -9. So we don't have to make a number line. We don't have to test to see if our critical numbers are relative extrema. We just need to include the critical numbers that are in the interval in our table and then figure out when I plug these numbers in, which is the largest and which is the smallest. Let's look at some more examples. The directions for these three problems say determine the global extrema. Global is just another word for absolute on the given interval. So we're going to start the same way that we've been starting. We're going to first find our critical values, or critical numbers. So derivative first. This is going to give me 3 times 2/3, which is just going to be 2, x to the -1/3 minus 2. And I'm going to rewrite this so that it's easier to see where it is 0 and where it is undefined. So this is x minus 2. So this is undefined when x is 0, because that would make the denominator of my fraction equal 0. So that's going to be one of my critical numbers. The other one I'm going to get when I solve for x when this is equal to 0. So I'm going to add 2 to both sides. It's going to give me 2 equals 2 over the cube root of x. I'm going to multiply both sides by the cube root of x. So 2 times the cube root of x equals 2. So x is going to be 1. So we have two critical numbers, 0 and 1. Those are both within this interval. So I'm going to look at all of the candidates that could be my absolute extrema. I'm going to have the endpoints, -1 and 3. And then I'm going to throw my critical numbers in there, 0 and 1. If I plug -1 into the original function, I'm going to get, and I'm going to do this work over here, f of -1 is going to be 3 plus 2. So that's going to be 5. F of 0 is going to be 0. F of +1 is going to be 3 minus 2, which is 1. And f of 3 is going to be 3 times the cube root of 3 squared minus 2 times 3 is 6. So 3 times the cube root of 9 minus 6. Now this is sort of an ugly number here, not very friendly, but we only need to know, is it the largest or smallest number on this list? So right now, 5 is the largest number on this list and 0 is the smallest number. So all that I really care about is whether this number is bigger than 5 or negative. If that is the case, then it is an absolute extrema. Otherwise, it's just another value in my table. So we don't know what the cube root of 9 is, but we can think to ourselves, what's the cube root of 8? The cube root of 8 is 2. So this is 3 times something bigger than 2 minus 6. 3 times something that's just barely bigger than 2 is going to be a little bit more than 6. Minus 6 is going to be a little bit more than 0. So 0 is definitely the absolute min. And that makes 5 definitely the absolute max. All right, I'm going to encourage you to pause the video and try and work through number 5 on your own. And I'm going to clean up some space so we have room to work through it. So find those critical values, make a table, and plug in each of those values to find the absolute extrema. Okay. So the first thing we want to do is find the derivative. We can find the derivative using the chain rule. So the derivative of cosine is negative sign, so this negative is going to become positive. And the derivative of the inside function is 2. So this is going to become positive 2 times sine of 2x. And if you're not seeing that, we're saying this becomes negative sine of 2x, and we multiply this by the derivative of the inside, which is 2, and that's how we get here. Now we want to know where this is 0 or undefined. It's defined everywhere. It will be 0 when sine is 0, and sine is 0 at 0 and pi. So and 2 pi. I want to know when is 2x 0, when is 2x pi, and when is 2x 2 pi. These are going to give me my critical numbers, which are going to be 0, pi over 2, and pi. So now I'm going to make my table with my candidates, x and f of x. I need to include my bounds, so 0 to 2 pi, and in between I have pi over 2 and pi. If I plug 0 into cosine of negative cosine of 2x, so I'm plugging things in here, 2 times 0 is 0, so negative cosine of 0 is 1, so negative 1 is what this is going to be. If I plug in pi over 2, I'm going to have negative cosine of 2 times pi over 2, which is cosine of pi. Cosine of pi is negative 1, and then I'm changing the sign, so that's going to give me positive 1. If I plug in pi, I'm getting negative cosine of 2 pi. Cosine of 2 pi is positive 1, and then it becomes negative. Same thing if I plug in 2 pi, then this just becomes a 4. Cosine of 4 pi is 1, and then we make it negative. Now, if you notice in this table, we actually have 3 of the same value. That's okay. This question isn't asking us for ordered pairs. It's asking us what the absolute max and the absolute min are. Well, the absolute minimum is negative 1, and the absolute maximum is positive 1. And that should make sense. What do we know about cosine? Cosine oscillates between positive and negative 1. So it makes sense that those are our absolute max and min. All right, let's make some more space for number 6. So go ahead and pause the video if you need to look back over that, and then we're going to get to our last example, and then we're going to recap what we covered in this section. All right, number 6 is intentionally tricky, but before we jump into it, I'm going to rewrite the original function, not the derivative, as a piecewise function. If you don't know how to do this, go check out one of the videos from chapter 1 that covers limits and derivatives, because we talk about it extensively there. So I'm taking the opposite of what I see here. That's true if x is less than or equal to 2. I'm choosing 2 because 2 is what makes the inside 0. If we plug in numbers that are more than 2, we get exactly what we should, because absolute value just keeps it the same sign. So here's our original function. If you think you know what to do now, I encourage you to pause the video and work through the rest of this problem. So what we want to do is find the derivative. We're going to find the derivative of each piece. So the derivative of this piece here is just negative 1. That's true if x is less than 2. I don't know if the derivative exists at 2, so I'm not going to write or equals 2. The derivative of this is positive 1. This is true if x is greater than 2. Now, if you remember from previous units, we can only have a line here if the limit or the derivative from the left and the derivative from the right are the same. Well, they aren't. One of them is positive and one of them is negative. So the derivative does not exist at x equals 2. And that should make sense. We're talking about an absolute value graph here. There's a sharp turn at that vertex, so it makes complete sense that the derivative does not exist when x is equal to 2. What does this mean for absolute extrema? It means that this is a candidate, and so are 0 and 5. Now, if there was no number, if there was an or equal to sign here, or if we didn't have a critical value, then our candidates would just be the 2 endpoints, and that's fine. So if we didn't have an issue here with 2, then my candidates would just be 0 and 5, and that's fine. So 0, 2, and 5. If I plug 0 back into my original function, the absolute value of 0 minus 2 is 2. The absolute value of 2 minus 2 is 0. The absolute value of 5 minus 2 is 3. So our absolute max is 3. And our absolute min is 0. So let's recap what we covered in this video. First, we reviewed how to use the first derivative test to find relative extrema and to find intervals on which our function is increasing or decreasing. So we find the derivative, we set it equal to 0, that gives us our critical values. We plot our critical values on a number line or on a sign chart to figure out where the sign is changing. And where the derivative is positive, our function is increasing, and where the derivative is negative, our function is decreasing. And where it's changing from positive to negative, that's where we have relative extrema. We then talked about the candidate test and how we first need to find those critical values, and then we need to test the critical values and the endpoints to determine what the absolute max and absolute min of a function is. So go ahead and write down any questions you have, post them below, and I look forward to supporting you on this. Thanks for listening.